Okay, hello everyone. Today we're having Claire Frechette, and she's going to talk about lattice model for supersymmetric LLT polynomials. Thank you everyone for coming.
Alrighty. Hi everybody, I'm Claire, and as Slava said, I'm going to be talking about lattice models for supersymmetric LLT polynomials or superLLT polynomials. A little bit of background about me. First, maybe I'm a 6th-year grad student at University of Minnesota working with Professor Ben Brubaker. I usually do slightly more things on the number theory end of lattice models, but for being interested in quantum groups and then from also being interested in running undergrad research projects, I've been doing a little bit more combinatorial stuff lately. So this project in particular is based on joint work that I did that I originally started as an REU project at the U of M, and then has morphed into a bigger project. So it's currently already up. There's a preliminary version on the arXiv. There's going to be a new version appearing very shortly, though, in the next week or so, hopefully. So a brief outline of the talk. We're going to start with an origin of this project and how it sits in the literature. Then we're going to move into talking about our main object, about what a supersymmetric LLT polynomial is. We're going to define a lattice model that will give it as its partition function, and then talk about the solvability of that lattice model and identities for our polynomials and how they interact with our lattice model. And there's a surprising solution to the Yang-Baxter equation at the end, or at least a surprise to me. So our opening introduction section is, where did this project start? It started as an REU, where our students constructed a ribbon lattice model that gave LLT polynomials, so not supersymmetric, just LLT. And they figured out the model for all n, then proved that it was solvable up to 3 and conjectured. And then they went back home at the end of the summer and it stagnated for a while. And this project I co-mentored along with my advisor, Ben Brubaker, and one of my collaborators, Katie Weber. Then in 2020, another team of researchers, Cortiel, Gitlin, Keating, and Meza, came up with a different lattice model that gave a very closely related set of polynomials called co-inversion LLT polynomials. These two models are very closely related by a bijection that relates the ribbon tableau to a different set of tableau that they were using to generate their model. In 2021, these projects were both subsumed by Agarwal, Borodin, and Wheeler's general lattice model. Then about a couple of weeks after we saw this paper come out, our students came back to us and said, oh, we finished the solvability, we fixed it. Not knowing that this general model had subsumed their original one. So I came on to the project, not just as a mentor, but also as a co-author to generalize our REU project to supersymmetric LLT polynomials and be able to use the solvability relations that they just come up with. So that's this project in particular. Then very recently, we just found out that the other team from the co-inversion LLT polynomials also generalized their model to supersymmetric. I haven't finished reading through this paper yet, but it looks like it's going to relate to our model in the same sort of way the other two, the original LLT models, related. So clearly this is an area that lots of people are working in and very excited about, and we expect that hopefully there should be implications for these super LLT polynomials in terms of other supersymmetric models that have come out recently as well. So now that we've got the literature out of the way a little bit, what's our main object? What is a super LLT polynomial? I'm going to go through the combinatorial background of this a little bit quickly. I wanted to make sure I had it all here in the notes for anybody seeing this talk later. So if you're very familiar with Tableau, you might be a little bored during this section. If you're not familiar with Tableau at all, I'm sorry that I'm going to go a little fast. But the basic object that we used for this, for our supersymmetric LLT polynomials, is a type of tableau based on what are called end ribbons. So you take a skew shape of partitions. If it has n blocks in it and is connected and contains no 2x2 squares, it's called an n ribbon. And we define a statistic on these that is called spin. that's based on the height. So it's the height of the ribbon minus 1. This should not be confused with the spin we frequently talk about in terms of lattice models. And I'm going to try in particular not to say spin when we're talking about lattice models so that you'll remember that spin only refers to this statistic. So I've got a couple examples here of 4 ribbons. This one's got height 3, then 2, then 1, and then 2 examples that are not 4 ribbons. The first one because it contains a square, the second one because it's not a skew shape. Given a skew shape or a larger skew shape, we can then tile it with different types of ribbons. And we're going to say that if we set an n, a tiling by n ribbons is a horizontal strip if the top rightmost square of each ribbon touches the top boundary of your skew shape. So here's one example that is and one that isn't. And a vertical strip if we have a tiling that flips over to make a horizontal strip. So analogously, the bottom leftmost corner has to touch the top boundary. And this is the context in which we originally defined the LLT polynomials. So as many types of tableau, we've got a notion of semi-standard here as well, which is that if you label your n ribbons according to some alphabet, the labels I have to form a horizontal strip. A note for the motivation behind this: if we set n equal to 1, so our ribbons are just single blocks, this is precisely the condition you need to recover semi-standard Young tableau. And then we can define a LLT polynomial named for Lescu, Leclerc, and Thibon based on as a generating function off of these tableaux. So this is where the spin statistic comes in. I take an extra parameter q, and I take q to the spin, and then my set of x's I take to the weight of my tableau, where the weight is the number of ribbons labeled with a particular I. So I have xi to the number of i's. A couple things to note about these functions is that they are symmetric. If you set n equal to 1, it turns out that q will be irrelevant because ribbons that are just boxes they all have height 0, and so we recover our Schur functions. And then if you set q equal to 1, we get a product of Schur functions. So these are a q-analogue that generalizes our Schur functions. Another thing to note is that they were called, up until fairly recently, they were called ribbon functions. So if you see that term kicking around in the literature, it does mean exactly the same thing as an LLT polynomial. But our object today is the supersymmetric analog of that, and this was first defined by Lamb, where given 2 different alphabets, we're now going to allow our ribbon labels to come from an original alphabet A and an alternate one, A prime. We're going to set a total order between them that respects the individual orderings. We're usually going to use the natural numbers. And we're going to define a super n ribbon tableau to be a ribbon tableau where ribbons labeled in our first alphabet make horizontal strips and the ones in our second alphabet make vertical strips. And then the skew shape that you get when you look down the total order of the labeling interacts properly. And we use these as a generating function to give us supersymmetric or superLLT polynomials. So as before, we have q to the spin, we have x to the weight in the first alphabet, and then we also have a parameter, second set of parameters, negative y, that we take to the weight in the second alphabet. You can also get this same process by, or this same polynomial by other methods related to taking supersymmetric versions of symmetric polynomials, but this is the one we chose to focus on for this topic because in particular, it's going to relate really nicely to our lattice models. So I have another example of a superLLT polynomial with the same shape as the one from before. And one thing, if you get bored during the rest of the talk and you need a toy example, one thing that you can notice in this is that while I picked a small enough example that it's hard to see that it's symmetric in the x and y variables separately, it turns out that these polynomials are independent of the choice of total order we picked. So frequently the two total orders we're going to pick are the whole first alphabet is bigger than the whole second alphabet, or vice versa. It turns out it doesn't matter at all. And Lamb originally proved this via an operator definition. We are going to give a lattice model proof of it later as well. So, and then the last thing I want to say about superLLT polynomials is that they encode the duality between horizontal and vertical ribbon strips very nicely. So one of the things we often care about when we look at tableau is how does a tableau and its conjugate interact, so the partition and its conjugate partition, and if you flip the whole tableau over, does it still give you a tableau that corresponds to the rules, the filling rules you've chosen? And it turns out that in for super ribbon tableau, it does. Your horizontal and vertical strips switch places, and you have to account for your spin by a very predictable factor. So we have a nice way to rewrite a tableau, a super LLT polynomial and the super LLT polynomial for the conjugate skew shape in terms of one another with just this correction factor. Okay. So this is a lattice model seminar. I should probably tell you about a lattice model. The original project that our REU students worked on all the way back in 2019 was taking these ribbon tableaux and figuring out how to think about this as a lattice. So the original inspiration that they used was looking at a particle interaction inside the lattice inside the tableau defined by edge sequence paths. So we're going to label all of our edges of your ribbon starting in the bottom corner, bottom left corner, going to the top right. And we're going to place particles on the vertical edges and holes on the horizontal edges. And then we see that when we connect up our particles, the most natural way to connect them up is that one of your particles travels from the top right corner to the bottom left, and the rest of them travel straight through. So if we think about this as a model where all the particles travel up this way. Oh, I have a laser pointer and I'm totally not using it. Right, we have this one particle that's going n steps and everybody else goes 0 steps. So to put this on a lattice, what we did was we can think about this in terms of n times 1 vertices. So I have n horizontal edges and 1 vertical edge at each vertex, which you can write, and some, I believe the Cortiel, Gitling, Keating, Mesa team chose more this path where you label your horizontal edges with an n tuple of choices. We picked a slightly different version where we look at our horizontal edges. They in fact come in 2 types. One is this twisted edge, and the rest of them we're going to call straight horizontal edges. And so then the condition we need to make sure that a particle travels through n steps is that we need to make sure that particles traveling along these straight horizontal edges don't change direction. They can't exit. So we say that a n ribbon vertex of this type is admissible if it follows the generalized ICE rule. So we're going to label with arrows. You need the same number of in arrows and out arrows. And then you also need the label to not change along these plane edges. It can only change at the twisted edge and on the vertical edge. So I'm going to give an example here at the bottom that this ribbon that we were looking at earlier. I know this is a lot of lines in a very short amount of space, which is why I tried to color them appropriately so you could see the interaction. The particles at 6 and at 2 travel straight up, and the particle going from column 7 to column 1 comes in here, traces out, and then exits out the top. And then we see that there are our two statistics. Our spin is going to accumulate anytime we have the traveling particle interact with one of our particles going straight up, and corresponding to these powers here. And then our we need to choose a vertex on which to account for the weight coming from the ribbon, and we chose the vertex where it ended. So the next thing we have to do for a lattice model, we're going to define a system of boundary conditions. I think if, oh, no, I've got my cartoon up here. Perfect. As standard, we're going to adjust our skew partition by a row shift. We're going to have R rows, where R is the typically going to be the length of both of our alphabets combined. We're going to have enough columns to label by lambda plus row, our biggest partition. We're going to label our side boundaries all going to the right. And then our top boundary will have up arrows on parts that appear in our smaller partition, and our bottom boundary will have up arrows on parts that appear in our larger partition. So I think of this as taking the N ribbon and stretching it and placing it on top of our partition function. As standard in lattice models, we also need to define a Boltzmann weight. If this is your first lattice model talk, I'm sorry I'm going a little bit fast through this, but we pick a Boltzmann weight for each type of vertex, and then we define the weight of a state to be the product over the weights of the vertices, and the weight of a system to be the sum over weights of states in that system. And this is also known as the partition function for that system. So a couple things we have to consider, and oh, there we go, for horizontal strips versus vertical strips and these are two very complicated horizontal and vertical strips. I wanted to make sure I got big enough examples that you saw sort of the weird things that can come out. In a horizontal strip, what I want you to focus on here is this red particle that is allowed to travel through, then back, then through again, because of the fact that we require top boundaries to the top square of the boundary to hit the top boundary, but we don't require the bottom one in a horizontal ribbon strip. So we need an option for that particle to continue through the lattice model, which corresponds to this vertex 5. In contrast, in a vertical ribbon strip, all of your particles, we see the traveling particle has to exit out. And so you don't want to allow that particle. So in particular, the vertex we saw here, 5, corresponds to a type northeast vertex. We don't want to allow that type of vertex for a vertical ribbon strip. So you wind up with two different sets of weights, a weight for horizontal ribbons and a weight for vertical ribbon strips. So I'll call them the horizontal strip weights and the vertical strip weights, H and W. And then we attach spectral parameters to our system in the logical way that we would think. So we're going to number our rows according to the total order, and rows that appear in our first alphabet take horizontal strip weights. Rows that appear in our second alphabet take vertical strip weights. And yeah, we've numbered our rows from top to bottom. So the main theorem of, or one of the main theorems of this paper is that given this set of weights, the partition function of our lattice model is precisely the superLLT polynomial. And the way that we proved that was by constructing a weight-preserving bijection between the super ribbon tableau and the lattice model fillings. Then one fairly immediate consequence from this lattice model is that we get a branching rule. Hello. I was a little worried we would have visitors during this talk. She doesn't know anything about lattice models. I'm sorry, she's not going to be very helpful. But we can get a branching rule fairly simply by choosing a place to cut our lattice model in half horizontally. We choose some space in between rows k and k plus 1. And we in fact see that the boundary conditions on the top half of that still correspond to a superLLT polynomial in fewer of our parameters. So if we set some like superset of our parameters, we're just going to call them all z's for a second, we're going to get the bottom end of our parameters appear in this piece that goes from gamma to mu. Oh, sorry, the top end of our parameters appear in this piece that goes from gamma to mu. That's right, we're numbering top to bottom in this model. And then the other half of our parameters appear in this piece that goes from gamma to lambda. And I wrote this as a sum over all partitions gamma, but in fact, most of these terms are going to be equal to 0 because the only non-zero terms are going to be the ones that correspond to super rip and tableau. And it's not hard to use the lattice model to write down a specific condition for which of those terms are going to be equal to, are going to actually show up. The one thing I will note about it is that we wrote it in terms of compositions, not partitions. So you're keeping track of an ordered list of what columns your particles are staying on as you're moving through the lattice model. So then the next thing we always ask about a lattice model is it solvable? And in fact, the superLLT lattice model we have here is solvable, which is very exciting. So if this is your first lattice model talk, this is one of the many Yang-Baxter equations we can care about. This is in particular the RST Yang-Baxter equation, where I'm considering S and T to be sort of horizontal weights. And I've got a diagonal vertex R here. And I want the lattice model or the partition function that I get when I attach this vertex on this side to be the same as the partition function of this system on the right. And if a set of 3 weights satisfy this Yang-Baxter equation, we call them solvable or integrable, and we frequently abuse notation and say that the model is solvable or integrable. And so it turns out that this lattice model is indeed solvable. In fact, any combination of the sets of weights that you can take 2 horizontal strip rows and swap them, 2 vertical strip rows and swap them, or horizontal and vertical strip row and swap them. And this theorem subsumes the conjecture that was left over from the RU report, because if you set your entire second alphabet to be empty, you're going to get back LLT polynomials, right? The super part of the supersymmetric LLT polynomial, you can ignore it and get back symmetric LLT polynomials. And the way that we're going to get solvability of this is via a fusion procedure. So we're going to take the R vertex that has n strands, because I had to connect it to n horizontal strands, and I'm going to split it up into pieces, sort of pair of strand by pair of strand. So I take the top piece, I split it off, and so on and so forth down the lattice, or down the vertex into these little pieces Rk. And then I say the weight of the whole vertex is the product of the weights of the pieces. So this corresponds to the fusion procedure you get when you take tensor products of quantum group modules. I'm not going to talk too much about all the details of that, but there is an algebraic motivation behind why this particular type of Yang-Baxter equation works, and it works because our original, R and T, or sorry, S and T weights are also fusion weights. And so then the particular choices of weights for our individual pieces we take are also going to look kind of nasty. I didn't make them so big so that you, because I did want to fit all of them to show them to you, but we catalog our different types of vertices that can show up. And then we see, oh, I should move that down a little bit, actually. There we go. And then we see that some of these weights are very nice, and some of them have a power of Q that you have to keep track of, where a vertex might be able to see other vertices in the big Rn vertex. So some of them will have adjustment factors, and this is because we have a spin statistic we want to take care to account for. If you set Q equal to 1, all of this goes away, and we get back into like very nice Yang-Baxter equations. And maybe one thing to note here is that the quantum group going on in the background is the universal enveloping algebra for affine SL of R1, the superalgebra, where R is the number of particles in your system, so the number of parts in your bigger partition. So the idea of the proof of solvability here is that we want to reduce, right, because, and this is part of the reason why the RU students got stuck in 2019, is because they were trying to account for all of the possibilities, but as n gets large, that's going to be impossible very quickly. Their computer stopped working at n equals 3. So what we do is we are going to notice the fact that on most of these edges, my label isn't allowed to change. So in fact, most of the edges in the R vertex, I'm gonna have fixed edges showing up here and here, as well as fixed edges from the boundary choices I get. So most of this R vertex is going to be the same on either side of my Yang-Baxter equation. It's only the part of it that's connected to the twisted edges that's going to be allowed to vary. And so we were able to reduce the proof to looking at the interaction between this underlying Yang-Baxter equation by just these 3 strands and a fixed block of the rest of the R vertex. And what winds up happening is that it boils down to checking that powers of Q that appear on both sides are actually the same. All of the terms that incorporate powers of X or of Y, it's pretty straightforward to check when Q equals 1, and then we adapt for the different powers of Q that were allowed. So then, now that we have solvability, we have a Yang-Baxter equation, we can go back to that proposition that Lamb proved using commutativity of operators, and we can give a lattice model proof for it. So superLLT polynomials are symmetric in our X and our Y variables separately, and they're independent of the total order. And the way we do this is by attaching a vertex on one side via our beloved train argument and shoving it through via the Yang-Baxter equation. So depending on what type of rows you pick, if you pick 2 horizontal strip rows, you'll get symmetry in X variables. If you pick 2 vertical strip rows, you'll get symmetry in those Y variables. And if you pick a different 2 different types, you get independence of total order. The way this comes from is the fact that since we picked toroidal boundary conditions, there's only going to be one option for this vertex, my R vertex, in each of my cases. So when I attach on the left, I get this R vertex of all east-facing vertices. I then get back my original boundary conditions and the weight of this. Using my Yang-Baxter equation, I shove it through to the other side to get the partition function for this system, but I see that the R vertex that shows up in that has to be exactly the same one I started with, and the weights of those 2 pieces are going to be equal. So this is going to cancel off, but I'm going to have switched my rows. So I'm going to get symmetry in those 2 spectral parameters. Okay. We're now going to pivot and look at the, Lamb originally proved the symmetry relation via operators. What other operator relations could we go back to and then try to interpret in terms of our lattice model? So the remaining identity I'm going to talk about for the rest of the talk is the Cauchy identity for LLT polynomials. And we're going to need a little bit of combinatorial background to get everything defined. So going back to the operator definition, and this is following Lamb's Boson-Fermion correspondence paper. I'll have the reference at the end of the talk if you want to go back through. A lot of this is based very closely on the same types of methods that he uses. We're going to define our 3 types of symmetric functions: homogeneous, elementary, power sum. And then we're allowed to take products of the power sum symmetric functions according to some partition lambda. And these, when we vary over all partitions, we get back a basis for the space of the ring of symmetric functions over the complex numbers. And in particular, if we expand our other types of symmetric functions in that basis, where we have a correction factor to account for being able to choose different ways to choose partition, we get that these are the expansions and that they're very closely related. You'll see, in fact, that the elementary symmetric functions are only off from the homogeneous ones by this power of 1 showing up here. We're then going to define a Heisenberg algebra using our symmetric function theory in the back of our head as motivation. We're going to take the associated, take a bunch of symbols AI and make the associated algebra with identity generated by symbols BK, where our K show up in are indexed by the integers -0, and our commutation relation is defined in terms of those AK. And you can do this very generally, but in particular, just for this talk, we're going to pick our AI, or I'm going to call them AK most of the time, to be a sum of products, a sum of powers of q. So I'm going to take 1 minus q to the 2n k over 1 minus 2 to the k. We're then going to construct elements of this Heisenberg algebra out of our symbols in the same way that we got our p lambda out of our power sum symmetric functions by taking products over partitions. And then we can construct elements analogous to our h and our e operators, analogous to those, by taking sums of these b lambdas. So we're going to have 4 types of operators running around: dk, d tilde k, uk, and u tilde k. And our non-tilde ones are going to correspond to h, where you can see here I've got the difference is that I've got a sign. And our tilde ones are going to correspond to e's. So Lam's Boson-Fermion paper deals solely in dk and uk, but it's not very hard to extend all of those methods to our tilde operators as well. This Heisenberg algebra then acts on the Fock space generated by partitions with inner product given here by our delta operator. And we can use this to define a pair of polynomials by acting on our operators on a particular partition and then taking the inner product against another one. And this will in fact give us skew polynomials defined on skew shapes. And in particular, given this choice of AI or AK, both of these polynomials are going to specialize down to our superLLT polynomials. So again, you can do a lot of this in much more generality, but we just want to look at these. And the idea behind the proposition part is that they specialize to our superLLT polynomials. The idea behind this is that half of our operators are adding ribbon strips, and the other half of them are removing ribbon strips. So my u operators correspond to adding horizontal strips, my u tildes to adding vertical strips, and then the d operators correspond to removing the same types of strips. And Lam's proof that the symmetry relations comes out of the fact that all of these operators commute with themselves, and that operators of the same type of addition or removal also commute. But the commutation relations between the other types of operators do not turn out to be so simple, and investigating those gets us a generalized Cauchy identity. So given 2 partitions, mu and lambda, if we take a sum over, or sorry, mu and nu, if we take a sum over lambda that lie above mu and nu, we can form a relationship between this and the sum over lambda that lie below mu and nu by swapping all of our operators subsequently past each other, and we're off by this commutation relation from this. And so this Cauchy identity was proved in various levels of generality at the same time by my group and also by my collaborator Andy Hart, who's on here, I can see, and then also by Agarwal, Borodin, Petrov, and Wheeler. And I'll have the links to these 2 papers below in the references as well. But for the particular choice of AIs that we picked, it's pretty, we're able to compute this commutation relation and this commutator, and in fact, we get this product over terms. And the thing I want to point out about it specifically is that it also involves a lot of these parts of these powers of q, but that variables that are acting in the same place, so my x versus my w are both in the first alphabet, give us terms that show up in the denominator. Same with my y and my z acting in my second alphabet, versus comparing my x's and my z's, for instance, is going to give us a term in the numerator. And this is going to correspond to the relationship between horizontal and horizontal strips and the relationship between horizontal and vertical strips. So this is in fact, precisely why, oh, no, waiting, save that for a second. This general Cauchy identity turns out to generalize both the Cauchy and the dual Cauchy identity for LLT polynomials, not the super ones, just LLT polynomials. And the way that this is frequently stated is for a n-core delta. So if you're not familiar with n-cores, think the empty partition. But you can, in fact, do it in more generality. I'm just going to state it in that version, though, where the Cauchy identity corresponds to taking two lambdas that lie over that n-core. So I'm allowed to form form ribbon tableau based on it. Gives us a product. When I compare horizontal versus horizontal strips, I'll get a product showing up in my denominator. Whereas dual Cauchy identity, the dual Cauchy identity asks the question when do you have the circumstance where flipping over a horizontal ribbon strip gives you a vertical one, and it's going to have finitely many terms, in fact, but we can use the same sorts of relationships we used up at the beginning to rewrite. Usually it's framed in terms of a partition and its conjugate, but we can use our superLLT polynomials to rewrite it in terms of a partition in itself by taking the second variable. So what this means is that there is no dual Cauchy identity for the superLLT polynomials. It's just corresponds to a change of basis of your original LLT polynomial. So we just get one Cauchy identity for superLLT. Okay, I think this might be a great place for me to pause for questions before I head into the last section. I know I went real fast, and I'm from New England, so I talk pretty quickly to begin with. Does anybody have questions? I haven't seen anything pop up in the chat.
I have one question that probably it would be more appropriate to ask at the end, but since you were given me a chance.
Okay.
So the supersymmetric version also is contained in Borodin-Agarwal-Wheeler.
I think you can, from what I understand from watching that talk, you can very easily extend their methods to get this supersymmetric model, but it wasn't actually in the paper yet.
Oh, okay. Mm-hmm.
Yeah, so their new supersymmetric paper that just came out, maybe I'll add that to the references at the end before I send you the notes. Their new supersymmetric paper that just came out is can eventually cover this, but it doesn't yet.
Okay. Okay, thank you.
Yeah. And in particular, I'm very curious to see if they have ideas about the YBE that's going to show up in the next section, because I don't understand where it comes from. I just know how to get it, and I would really love to understand where it comes from. Okay. Any other questions? No. Okay, then I'll roll along to the end of the next section. So this is our final section for the day, and this is, in my previous example, earlier on, we were able to take a identity proof via operators and make a lattice model inspired by it. What happens if I take the same sorts of ideas from my operator proof of the Cauchy identity and I mimic these on the lattice model? So my original model adds strips from U to get to lambda. There's a full second set of operators that remove strips. It should be analogous to make a model that also corresponds to removing those strips. So we're going to define an alternate system of boundary conditions that amounts to switching the direction that all of your particles travel. So we're going to switch our side boundary toroidal conditions to point the other way. We're going to switch our top and bottom boundaries, and we are going to switch our weights to account for the fact that we are switching all of our direction of particles. But they're going to be effectively the same weights, just the arrows are going to look a little bit different. And it turns out we have to switch these side boundaries in order to maintain the ice rule. I tried very hard to not have to switch them, and it was not going to work. And then we're again going to number our rows from top to bottom according to a total order. So our little cartoon of how this works looks like this, where in our previous model, particles traveled diagonally this way, and now they travel diagonally the other way. So my comparison here with our new alternate model versus our original model state is that you can see, if you compare real quickly the partition function weight that shows up from the weights, in fact, all of my vertices are designed to have exactly the same weight that they did originally. But if we, for instance, follow this blue particle or teal particle that travels through my top state, it corresponds to this red particle traveling through my original model. And I've switched my boundary conditions. You can check that lambda here is the same as lambda here, and mu on the top is the same as mu on the bottom of the original model. Oh, I think maybe actually I have these flipped. Might remove and add. I'll fix that before I send you the notes, because our original model is supposed to remove strips from mu to lambda, so I've just got them labeled wrong. But as in the first, and these are in particular the weights we pick. If you glance really quickly at them, they're very, very similar to the ones that I showed you earlier. The only thing that really looks different from the tables, honestly, at a very quick glance, is the fact that I've got tildes on them. And it's, in fact, because it is the same model, I'm just reframing it in terms of a different modality. So proving that this model also gives the superLLT polynomials is effectively the same proof as the original one. And the reason I've constructed this new one is because I want to stack them together in the same inspiration as other Cauchy model, Cauchy identities formed out of lattice models. We're going to try to stack the one on top of the other one, and then we'll be able to cut apart on the area in between them. And if I look at the partition that shows up on this in between column, and I label it lambda plus plus rho, what I'd like is that the partition function of the top bit gives me one LLT superLLT polynomial, and the partition function of the bottom bit gives me a different superLLT polynomial. So there are a couple details that we have to take into account first. One of them being that each of my models already has 2 alphabets and a total order. I need a total order in order to number all my rows that respects both of the total orders on my models and all of the individual orderings. So I'm going to call this an overarching total order on all of my alphabets that combines the 2 types of alphabets that I have coming from my original model and my alternate model. The other thing that we have to take into account, since we're trying to match up with the Cauchy identity we showed earlier, is that in order to get all of the possible summands, all of the possible partitions lambda that show up in those Cauchy sums, we have to take into account the fact that horizontal ribbon strips can be arbitrarily long and vertical ribbon strips can be arbitrarily tall. So the lambda corresponding to them for horizontal strips, I can have my parts be arbitrarily large, and for vertical strips, I can have arbitrarily many parts. So a finite lattice model is only going to work in a case where I only have finitely many terms showing up in both of my sums. So in particular, when you have only horizontal strips versus only vertical strips, or vice versa going on. So you're winding up in the dual Cauchy identity for normal LLT polynomials. And the way that we get around this is by defining a semi-infinite model based on the idea of the Dirac. So taking inspiration from the operator definitions, we are going to have infinitely many columns. We're going to have an infinite sea of particles on the left, an infinite void of particles on the right, and in the middle, we're going to label according to our partition. So I'm going to define an overarching total order on all my alphabets, and I'm going to take 2 partitions in order to label the top and the bottom, and then I'm going to define a Cauchy model system with infinitely many columns labeled in the integers. I'm going to label my rows from top to bottom according to this overarching total order, and then I'm going to label my side boundaries according to which alphabet I'm showing up in, whether I'm looking at the original model or the alternate model. And my top and bottom boundaries are going to have up arrows on parts that show up in their partition. So I'm picking mu on the top and nu on the bottom, but then they're also going to have up arrows on all of the non-positive columns. So on all my infinite C to the left. And this is going to allow us to get all of the possible vertical ribbon strips that might show up, whereas having that infinite void to the right allows our particles to travel artificially or arbitrarily far and gives us all of the possibilities for horizontal strips. And then I pick all of my weights to correspond to the alphabet that the row came from. So if I'm in my original model, I've got weights H and V, horizontal and vertical strips. And in my alternate model, I have my tilde rows. So then it's pretty straightforward just by cutting our model in the middle, in between our original and alternate model. I have sort of two orderings that, two overarching total orders that show up in order to look at the Cauchy identity. We have the one where our original model is on top. So all of my original alphabets are less than all of my alternate alphabets. And in this one, when we cut, our lambdas that show up here show up above mu and above nu. Versus if we switch the ordering entirely, we put our alternate model on top, right? The alternate model has smaller partitions on the bottom than the top. So our lambda that appear in the middle are going to appear, whoop, got a typo right there. Mu and nu should never interact. Mu over lambda, there we go. They're going to appear below mu and nu. And in particular, we also notice that the roles of our spectral parameters change to, with respect to mu and nu. So then the question, of course, anytime you start with a lattice model is this solvable? Because what I would really love to have is a train argument with a Cauchy braid formed out of r vertices of the solution for this Yang-Baxter equation, so that I can attach it on one side, shove it all the way to the other side, flip my models, and get out my Cauchy identity with these two sums that showed up in my last result. However, or maybe I should say first, the short answer is yes. The long answer is it's kind of complicated. So the short answer is that yes, given these sets of weights, any combination of these sets of weights, there is an R vertex that satisfies the YBE. So I can pick horizontal and vertical strip rows in my alternate or my original model. Any combination of these works. The more complicated part of the answer is that it doesn't appear to come out of a fusion procedure like my R vertices showed up before. Right before, if we recall, we had n different pieces coming out of my R vertex, and these little R vertices, their product gave my weight. And they might depend on the other vertices, but they depended on the vertices in terms of powers of q, and they all sort of have an equal weight in the system. What shows up here is a very weird sort, or at least I think it's weird. I would be very interested to know if anybody knows the algebraic motivation behind this, that if one particular pair of vertex types appears, their weights change in a way that is not the product of their weights. We get additional terms showing up, and only the first instance of those two vertex types that show up do that. But all of the other vertices, their weights multiply together the same way that we would expect normally. So my example that I'm going to do here, because showing you the weights for all of these would be a lot. They're not particularly nice, but they're also not particularly nasty. They just have a lot of parameters you have to keep track of. So here, if I take the Yang-Baxter equation, that corresponds to switching a vertical strip row in my alternate model past a horizontal strip row. In my original model, the R vertex that I come up with, most of my pieces are a power of q times something in x and y, and then I see a term like the ones that showed up in my Cauchy identity showing up on one of my vertices. And these factors tau and kappa depend, again, count vertex types that show up below or after. But if I have an instance where a vertex of type north-north appears above a vertex of type south-south, they collect together into this weight here, which you can check is not the product of the weight of type south-south and the weight of type north-north. This middle term is in fact the only part of it that I want to show up. But in order to satisfy the Yang-Baxter equation, you have to wind up with these extra powers of q. And then the rest of the vertex completely ignores this interaction and fuses as normal. So if I have a situation where, for instance, I have counting R1 down to R4 in n equals 4, a type W vertex, a type NN, a type south-south, and then a type south-south, the W and the S fuse normally. This type NN and type south-south fuse together into this weight here. And then the three of these pieces fuse together. Whereas if they had showed up in the other order, they wouldn't have fused together at all. I would have had, or pre-fused, I would have had normal fusion, multiplying of weights. And if an additional instance had showed up, say I'd had another north-north and south-south vertex, only the first copy would have fused together. So I don't think I left room for this actually, but maybe, nope, I do not have room for that here. But I'm going to shove it in there anyways. If I had had this show up, I would have had one copy pre-fuse, and then the other copies would have stayed by themselves. And my question, the big question I'm left with at the end of this paper is, where does this come from? Is there an algebraic object that corresponds to this process of this like strange pre-fusion in the same way that fusion corresponds to a tensoring of quantum group modules? And one of the particular reasons why I was wondering about this is that you do not see this happen in the supersymmetric Schur case, because in particular, right, that's going to come from setting n equal to 1. And these q's, these powers of q that pop out are going to be equal to 1 and cancel off. So I'm not going to get this complication in supersymmetric Schur, but it's entirely possible I get it in other supersymmetric functions. And it would be really interesting if it had an algebraic motivation behind it. So in the last 5 minutes, I'm going to bounce really quickly back to the Cauchy identity and end on a conjecture, which is that precisely that the Cauchy model gives you the Cauchy identity. Most of your terms from the commutator show up on this side, in fact. So coming out from, my right-hand side above. And on my left-hand side, I'm going to wind up with part of the commutator, again, this sum that I would like, but then also since it's an infinite model, we wind up with an error term that has infinitely many powers in your variables y and your variables z. There's a way to, if you set up the entire process with your Cauchy braid on the other side, you get this error term is in the variables x and w instead, but it works out pretty much exactly the same. And the proof, the trouble we wind up in the proof, the only problem is actually the existence of this prefusion in the Cauchy braid. The fact that the model is infinite doesn't wind up causing a problem because most of the infinite part of it is weight 1. But in order to keep track of when particles are traveling through the Cauchy braid, you either have to do a lot of very tedious combinatorial bookkeeping, or we need to understand the algebraic motivation of where this strange YBE is coming from better. So, oh, and then if you wound up in a situation where you didn't have all of your different types of strip rows to be taking into account for, the error term does disappear, which is going to give us back the Cauchy and dual Cauchy identities for LLT polynomials on the nose. And I had mentioned this about attaching the Cauchy braid on the other side. This error term is coming from vertical strip rows, allowing a particle to travel infinitely far. If you attach on the other side, you get an error term from horizontal strip rows, allowing a particle to travel arbitrarily far. So I'm going to end with the future directions I'm interested in on this project. The first being, where does this YBE come from? I'm very, very curious. And the second being, do other supersymmetric functions also produce YBEs with this kind of behavior? The supersymmetric Schur functions, as I mentioned, are way too nice for this to arise, but maybe other polynomials that come out of Hamiltonian operators might, and that may give us more traction on the first question. So I'm going to end there. I've got a page of references. If you're curious about the arXiv numbers for most of these, I'll make sure to add in. Oh, nope, I've got the supersymmetric one here already. Perfect. This is the supersymmetric function paper that Slava had mentioned in his question. But if you're curious about any of these, most of them are recently up on the arXiv within the last year or so. And so we're still waiting on figuring out where they're going to be published. But it's very exciting, and lots of people are working on this at the same time. So I'm curious to see what we come up with next, because it's really interesting. So I'll maybe end there. But yeah, I really do want to know if you have any leads on where these YBEs come from. Please tell me. I'm very curious.
Okay, let's thank the speaker.